So when you've got chlorine molecules next to each other, they contain electrons. And those electrons are constantly moving. And at any given moment in time, instantaneously, they could shift and move to one side of a molecule or one side of an atom versus another. And if they do that, let's say the electrons are shifting in this direction, wherever the electrons are more concentrated, you will get a partial negative charge in that region and then a partial positive charge where the electrons have suddenly left. And these charges, these positive and negative charges are constantly coming and going. And these interactions between the molecules from the partial negative and the partial positive ends, they influence the electrons in neighboring molecules as well. So the electrons that had shifted to one side of a molecule will now shift to another side in a different molecule adjacent to it, because if there is a partial positive end on one side of a molecule, electrons which are negatively charged will be attracted to that partial positive end. So now I have a partial negative on this end of the molecule with a partial positive on the other, and this interaction in between them is my London dispersion force. This instantaneous dipole within the molecule induces the dipole in the neighboring molecule, and that's how I get this London dispersion force. Now, all molecules have London dispersion forces. All atoms have them. They are the weakest of the intermolecular forces, but if you only have a nonpolar molecule, then it will only have London dispersion forces, whereas a polar molecule will have London dispersion and dipole-dipole forces. But if it's a polar molecule with an HF, NH, or HO bond, then it will have hydrogen bonds as well as London dispersion forces. So the strength of these London dispersion forces is going to increase as the size of the molecules increases, because when you have large molecules, then the electron clouds are going to be more loosely held, so they have more movement, more ability to kind of like deform or polarize, and then if you have a more surface area in a molecule, it will also have more stronger London dispersion forces. And the shape of the molecule, which is going to influence surface area, because the electron clouds may be more spread out, will also influence it. So if I'm looking at, for instance, on this next page, if I'm looking at fluorine, chlorine, bromine, iodine, and astatine, as I go down this group, this is group 17, and as I go down the group, the mass is increasing, and the size of my atoms is increasing, which means two things. As the mass increases for nonpolar substances, the intermolecular force strength increases, and also as the size of the atom increases, the electrons that are in the outermost shell are being held looser, or loosely, I should say, by the nucleus, since they're so far away, which means they have greater polarizability and you would have stronger London dispersion forces. And you can see this manifest itself in the melting and the boiling points of the substances, because they are increasing as you go down that group. Okay? Now, let's talk about ion dipole forces. This is an important interaction when you have an ionic compound dissolved in water. Now, ionic compounds are held together by ionic bonds, which are attractive forces between a cation and an anion, or oppositely charged particles. And when you have your salt, which is an ionic compound dissolving in water, the ions are going to be attracted to the polar ends of the water molecule, and that is going to cause an ion dipole force. So as the crystal structure of the ionic compound starts to break down, while you have that salt dissolving in water, you're going to have cations and anions freely moving. So you're going to have, for instance, sodium ions and chloride ions freely moving within water. And then the negative oxygen ends of the water molecules are going to surround the cations. So here is your sodium cation surrounded by the negative oxygen end of water because it has a partial negative charge on it. So there's an attraction between the partial negative end of water and the positive charge on the cation. So that is your ion dipole force. And then you're going to have the anions surrounded by the hydrogen end of water because, so here is your chloride ion, this is your anion, surrounded by the hydrogen end of water because the hydrogen end of water is partially positive. So that interaction between the partially positive hydrogen and the negative anion, that is also your ion dipole force.